This diagram shows that the density, pressure, and temperature of the air are greatest at sea level, decreasing with altitude increase. Sea level pressure at any point on the Earth's surface is caused by the weight of air above that point. The decrease in density of the air with altitude increase is also due to the lessening of the weight of air above any specific point. Because the heat in the atmosphere is radiated from the surface of the Earth, the greater the altitude, the further away from the source of radiation, the lower will be the temperature. In order that an engine's power output can be checked in any part of the world, regardless of the ambient conditions at that place, manufacturers specify a set of standard maximum power RPM figures which are obtained on a standard day, according to sea level ISA conditions. ISA stands for International Civil Aviation Organization, or ICAO, Standard Atmosphere. From the diagram, we can see that the sea level ISA conditions can be said to exist at a temperature of plus 15 degrees Celsius, a pressure of 14.69 pounds per square inch, which is the equivalent of either 1013.25 millibars or 29.92 inches of mercury, or 1013.25 hectopascals, and a density of 1,225 grams per cubic meter. The density of the air directly affects the performance of any aircraft. A reduction in air density results in lower engine power, which directly affects the length of the takeoff, the landing run, and the rate of climb. The air density is not only affected by the altitude. The local air temperature will also have a direct effect on it. If the temperature of an airfield is higher than the ISA temperature for the airfield elevation, then the air density will be lower in value than the standard, and thus the density altitude will be higher than the airfield elevation. So, whereas pressure altitude, in aviation terms, is the indicated altitude obtained when an altimeter is set to 1013.2 millibars, or 1013.2 hectopascals, density altitude is used to describe how dense the atmosphere is in comparison to the international standard atmosphere. It is the altitude in the standard atmosphere at which the prevailing density would occur. We can either employ a navigation computer to determine the actual density altitude, or use a simple formula. The formula requires that we add to the pressure altitude 118 feet for every degree Celsius that the actual temperature is above ISA. For an example of how much influence the temperature can have on the density altitude, let's try an example. Imagine that you're fortunate enough to be taking off in a light aircraft from Calgary, in Alberta, on a nice summer day. The indicated outside air temperature is plus 33 degrees Celsius. The elevation of Calgary Airport is 3,550 feet. And the QNH on this particular day is 1013 millibars, or 1013 hectopascals, which makes our pressure altitude also 3,550 feet. The ISA temperature for that pressure altitude is approximately plus 8 degrees Celsius. So the ISA deviation is plus 25 degrees Celsius. Substituting in our formula, if we multiply the ISA deviation, plus 25, by 118, we get 2,950 feet, which we add to the pressure altitude of 3,550 feet. That makes the density altitude at Calgary Airport on this day 6,500 feet. Remember that engine performance is associated with the density altitude. The higher the density altitude, the lower the engine performance. In the engine's general lesson, we stated that obtaining the maximum power output from a piston engine depended upon us getting the maximum weight of the air-fuel mixture, or charge, into the cylinders during the induction stroke. Unfortunately, as we've just seen, as the aircraft climbs to altitude, the density of the air reduces. Because of this, we have to reduce the weight of fuel in the mixture to retain the mixture strength at an optimum figure. This, coupled with the fact that the pressure available in the atmosphere to assist the flow of mixture into the engine cylinders is reducing in the climb, means that less and less weight of fuel is fed into a normally aspirated engine as the aircraft gains altitude. The term normally aspirated, when it's used to describe an engine, infers that the air being induced into the cylinders is not artificially compressed. The problem of the power output of an engine decreasing with increase in altitude can to some extent be overcome by the use of some form of power augmentation device. This device usually takes the form of a supercharger, which allows additional air and fuel to be fed into the cylinders at altitude. This results in the weight of charge, and thus the power, being increased. The power output of each engine is specified by the manufacturer. Having said that, however, each manufacturer also gives various power outputs which may either be obtained at specific engine control settings or used for limited periods of time. Takeoff power is the maximum power the engine can develop. Its use is normally time-limited. The maximum continuous power the engine can produce is called rated power. This power is produced at a specified RPM and boost, or manifold absolute pressure. We'll talk more of manifold absolute pressure later in this lesson. The aircraft is normally flown in the cruise at a fraction of this power. The maximum altitude at which the engine can maintain rated power, with the throttle valve fully open, is termed rated altitude. The pressure within the induction manifold of a normally aspirated engine at full throttle is slightly less than atmospheric pressure. This is because of intake duct losses and the pressure loss which even an open throttle valve generates. We've already seen that the manifold pressure decreases with any increase in altitude. Engine power output of a normally aspirated engine, therefore, decreases with altitude. There is, however, one bonus which can be gained through climbing the aircraft. The ambient pressure decreases as the aircraft climbs, and it is this ambient pressure, or back pressure, which resists the escape of the waste gases from the cylinder during the exhaust stroke. It is this same pressure which dictates that the piston has to waste energy in driving those gases from the cylinder during the exhaust stroke. As a consequence of the reducing atmospheric pressure, some of the power wasted during the exhaust stroke is reduced during the climb, due to the more efficient scavenging of the cylinders, which results because of reduced back pressure with increasing altitude. In order to either increase engine power for takeoff and initial climb, and/or to maintain engine power at high altitude, the inlet manifold pressure must be raised artificially, and this is done by supercharging. Where a supercharger is used to increase the engine power output at sea level, rather than to maintain normal engine power output up to a high altitude, the engine will need to be strengthened in order to resist the high combustion pressure. This type of engine, like the one shown here, is fitted with what is called a ground-boosted supercharger. Superchargers capable of maintaining sea-level values of power up to high altitude require a control system to prevent excessive pressure being generated within the engine at low altitude. Engines with this type of control system, similar to the one shown here, are fitted with altitude-boosted superchargers. Both the Roots-type compressor and centrifugal compressors are used as superchargers on aircraft engines, although the centrifugal compressor, because of its relative simplicity and ease of manufacture, is more commonly used. Although the compressors may be driven by either internal or external means, in fact, in some installations a combination of both internally and externally driven compressors may be used. Externally driven superchargers, which are known as turbo superchargers or turbochargers for short, are driven by a turbine which is rotated by the exhaust gases. Externally driven superchargers compress the air. Internally driven superchargers are driven through gearing from the engine crankshaft. Internally driven superchargers compress the mixture. The methods of operation and control of these two types are quite different, and are dealt with separately.